Okay, last time we talked about the idea of what a limit is and how we can use this idea to solve a certain problem that we called the tangent problem, and we sort of expanded our intuition on it to talk about the velocity problem first. Today we're going to expand our intuition a little bit further. We're going to make a few definitions, so have your pen and paper ready to write things down. Pause this video as you need to. Sorry about that. And let's actually go down to it. The idea here is that we're going to talk about the limit of a function. To find the actual tangent line of a function of a graph, right, which is something we discussed, we need to study limits more heavily because we came up with a strategy, right? We're going to pick 2 points and make the second point as close to the first one as we wanted. And for that, we're going to use limits, right? That way, the secant line, which is the line that goes through these 2 points, gets closer and closer to the tangent line, which is the line that just goes through P and not Q, right? You can go ahead and rewatch the previous video if you need to. Okay, let's use some calculations, some computations to actually do this. I'm not going to do this math here. I'll just walk you through it because this is basically what we did for the velocity problem. But let me just walk you through what's happening here. First, this slide here is walking you through the idea of investigating the behavior of this function here. Right, so x minus 1 over x squared minus 1. Okay, and looking at this function, first thing that you notice, if you got your Math 141 nailed down, is that 1 is not in the domain of your function. So that means f of 1 does not exist. But what if, this is a function that in real life, measures something that I need to know for x values close to 1, Maybe 1 will never be achieved, but I'll get very close to 1. I want to know what happens, right, when I get close to 1. Maybe I need to know that. And that's the idea. So here is what's being done. They're choosing x values. So if I plug in x equals, 0.5, what I'm doing here, and this is what I called 1 in the last slide, in the last video, actually, previous video, 1 was going to be, f of 0.5. So this will be, 0.5 minus 1 over 0.5 squared minus 1. If I plug that into a calculator, that's going to be this thing right there, right? 0.6667. I got 2/3. But that's not what I want. It's pretty far from 1 still, right? 0.5 is pretty far from 1. So maybe I choose, 0.9. So I calculate f of 0.9. So my second approximation could be, f of 0.9, and that will be 0.9 minus 1 over 0.9 squared minus 1. Plug that into a calculator. What I get is this. It's going to be my number 2, my second approximation. And I keep doing that, right? Getting closer and closer to 1 as I want, and this is what this arrow is telling you, right? That we're getting closer and closer to 1, and this number here is getting closer and closer to 0.5, as you can see, right? You can see the same thing happening if I choose values that are larger still than 1 rather than smaller than 1, because here was like 0.9, 0.99. Here I could do like 1.1, 1.01, 1.001. That was closer and closer to 1 still. I still get values, outputs to my function closer and closer to 0.5. So how do I express this? And if you look at the graph, right, if you represent this graphically, you can see that at 1 there's a little hole in my graph, and this hole happens at 0.5. Okay. Listen to this wording here. As x approaches 1, f of x approaches 0.5. As x approaches 1, f of x approaches 0.5. We're going to say this many, many times before. Okay? Many, many times again. And rewrite it in this way. So now I'm telling you what this means, right? When I write this, I'm actually saying what's highlighted in yellow in the previous slide, okay? The way you read this is you say the limit of the function f of x. You don't have to say the whole function, the whole like expression. You don't have to say this. The limit of the function f of x as x approaches 1 is equal to 0.5. And you write it this way, the way that I boxed. This is very, 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 very important. Take a second to look at this, to look at the main, important points. This is something important they can't forget. You cannot forget to write limit. You cannot forget to write the expression. And, maybe you don't write the result because you're still calculating the result. But, this thing here is an entire block. All these things together, they're one thing, okay? All these little parts. The x pointing to, with the arrow pointing to 1, the limit, the word limit, right, or the abbreviation limit, and the expression, they all go together, and the result of this is 0.5. Okay. So far, we haven't shown a way to actually calculate this. There is a way, but we're going with the intuition. We're going to do this for the entire slideshow of this video. Okay, let's keep going. So, bunch of words here. Let me walk you through the most important ideas. This is the intuitive definition, like I said today's intuition. So the limit of, we say this, right? The limit of f of x as x approaches a equals L. So x approaches L, f of x equals to L, right? This is how you say this. And this is the intuition. As we choose x values closer and closer to a, but not equal a, and that's important, right? The f of x gets closer and closer to L. Okay? This is an important idea too, but not equal a. So when we're getting closer and closer to a, in the previous example that was 1, right? We did not choose exactly 1 because then we couldn't. And we're using limit to solve something that we can't do, right? So we're defining as something that does not allow you to plug in the exact a value. Okay? You can also write it something like this. This is fine too. This means the same thing. So f of x approaches L as x approaches a. Just, again, take a second, write it down, familiarize yourself with this to understand what it means when you write this. Just gotta remember, always, 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 not equal to a. That's important. When we're talking about a limit, x is getting closer and closer to a, right, in this bottom part here, but it's never equal to a. Just because, like I said before, we may be dealing with situations where, like we said before here, 1 was not in the domain of the function. 1 is not in the domain of the function. So you can't plug in 1. If you could, there would be no reason for us to even have this discussion. You just plug in 1 and you find out what's going on, right? Okay, let's keep going with this. Talk about it graphically. Figure 2 shows the graph of 3 functions. Note that part B, f of a is not defined, and in part C, f of a is not L. Look at this. Let's talk about each of those separately. On A, if I choose an x value, let's say this is x, right? F of x is this guy over here. And this is, you can tell it's very close to L, right? F of x. If I wanted to choose, do a different color, a different x that's closer to a, even closer, then you could tell that f of that second x is even closer to L. And that's the idea, right? The limit is just f of a in this case. Here, though, right, there's a hole, meaning this f of a does not exist. For some reason, a is not in the domain, which is what happened with f of 1 in the example before. So still the same thing happens. We're getting closer and closer to L, but L is not f of a, right? Because f of a is not defined because of the little hole. And here, f of a is defined, but it is defined as something different. So this is f of a in this example. Okay. And same thing happens. The limit is L, but it is not f of a. So here, L is not f of a on C, and here, f of a is not defined. So the fact that it's not defined makes a huge difference for us. Makes a huge difference. Or that it's different from L is the reason why we always say, do not plug in A. Always plug in values close to A, but not A. Okay? Turn up the volume a little bit. Okay. Okay, I think that's good. And in all three cases, even though we had these issues, f of a was kind of different, sometimes not defined, sometimes far from L. In all three cases, the limit of f of x as x approaches a equals L. Okay, try and work on this and get the intuition very solidly. Let's do an example. Okay, let's do a graphic. Let's do it numerically, just like with the velocity problem. Maybe a little bit boring, but hang around, trying to understand the idea. So let's guess the value of limit of sine x over x as x approaches 0. Why do we need to guess it, right? We cannot make x equals to 0 because of this. We cannot divide by 0, right? So that means x equals 0 is not in the domain, so we can't plug in x equals 0, right? Okay, that's the first issue. We want to know what happens when x approaches 0 to this expression. So we're going to call it f of x. That's what this text is saying here. This text box is saying that f of x equals sine x over x. That x equals 0 is not in the domain, so we're going to choose values that are closer and closer to f of closer and closer to 0, right? And then we're going to do a little bit of math and find out. Okay, so let's say, let me move on to the next page, and let's choose some x values here and do a little bit of math together. I have my calculator on me. You may want to have yours too, or use some other computer algebraic system that you need. So here I want to find f of 1, and f of 1 will be sine of 1 over 1. Remember that whenever we're using sine of x is supposed to be in radians, not in degrees, so maybe you need to change that setting in your calculator. Let me see if mine is correct. So this will be, in my calculator, sine of 1 divided 1, and that will be, I think I have it in degrees. So let me change that to radians, and I'll be right back. Okay, let me continue. Sorry about that. So I'm doing sine of 1 divided 1, which is just does nothing with it. 84.14. I guess I'll stop at like 84.14. How many decimal places do they want? Let's say 8 decimal places. So like I said, it's going to be a bit boring. I'm not going to do all of these. I'll go like the first 3 or 4 so you understand what I'm trying to do. Say 84.147098. So let's do f of 0.5, just sine 0.5 over 0.5. So I'll do that in my calculator. So that will be sine 0.5 close divided 0.5. So that will be 0.95 9588 or something. So just write the whole thing here. 885107. And you can keep doing that, right? I'll go further. I'll go like here, 0.1. F of 0.1, 0.0, yeah, 0.1 is fine. Because 0.1 is very, very close to 0. Remember, we're trying to get closer and closer to 0, right? We're trying to get an estimate of f of 0. And I use quotation marks because in reality, we cannot actually calculate that. But I'm trying to get closer and closer to 0 in x values because those are allowed to be plugged in. So I'll do sine of 0.1 over 0.1, and that will be sine of 0.1 divided by 0.1, and that will be 0.9983 or something. 9983 3416, just because they're asking for 8 decimal places, I want to write the whole thing that I found in my calculator. And look, as you notice, if you try and do f of 0.01, right? And this is the last one that I'll do, let's see. So it'll be like sine 0.01 divided by 0.01, and that will be, look, 0.9999833. So it's very, very, very close to what do you think? Give it a second and think about it. Pause if you need to guess. But as we make x get closer and closer to 1, this value here of f is getting closer and closer to 0. This value gets closer and closer to 1. So basically what we're saying, we have the answers here, is that, I write with my own handwriting so you see the process of me writing. So it's limit as x goes to 0, sine of x over x, that equals to 1. That is sometimes called, and this is going to be used again, I'll refer to this as an important limit. So this is the fundamental trigonometric limit. Using this limit, we can kind of follow other limits that exist and that we're going to use. Okay, so here we go. We can't find f of 1 precisely. It doesn't exist. But as you plug in x values closer and closer to 0, we can find f of 0 precisely. But as you plug in x values closer and closer to 0, you find that the value gets closer and closer to 1. So you can assume that f of 0, if existed, should be 1 to make things work precisely. And on the right, you see the graph here, right? Take a second, think about this. Again, starting again, this is an important idea because now we're going to add a new one, which is the idea of one-sided limits. They work more or less the same way, but now we're restricting which x values you're allowed to plug in to just x values that are greater than 1 or x values that are less than 1 or less than 0, greater than 0, whichever value that you're calculating the limit of. So let's talk about this function here. This is called the Heaviside function. In high school, many people call this a step function. I don't like this notation, but I write it in case you need a familiar term to remind you of this is. This is the Heaviside function. Heaviside is the name of the guy that talked about these first. And basically, the graph of this, if you were to graph it, let me see if I have a graph on the next page. The graph of this would be something like this. So for t less than 0, the graph is this. And I got an empty circle because this is less than and not less than or equal to. And for t greater than 0, you have at 1. So 1. This is the graph of the Heaviside function at 0. And as t approaches 0 from the left, right, if you choose like t values over here, t very, very close to 0, right here is 0, right here. If you choose a t very close to 0, then h of t is very, very close to 0. It's exactly equal 0, but just to keep the wording, we say very close to 0. Just actually as close to 0 as it could possibly be. And here, as t, gets, if you choose a t value that's on the right of 0, then h of t, h of t here equals 1, whereas here, h of t equals 0. So it depends on which side you choose, okay? And that's how the idea of one-sided limits comes from. So we write more or less the same way, but we put like a little negative sign like on top of the 0 as if it were like a 0 raised to the negative power. We don't say that, but it's the same, like a superscript. And we put a plus sign if that were coming on the right side. And this is like on the left side. So this is to say you're only allowed to plug in t values that are less than 0 here on the left side, and the right side is you're only allowed to plug in values that are more than 0. Okay. So this is what this slide is saying. Let's look at the definition here. Again, this is intuitive. We're not going to use this definition for long. We're going to sort of go to a more mathematically heavy definition soon, but follow the intuition for now. The left-hand limit, or the left limit, or the limit of f of x as x approaches a from the left equals to L. So the closer x gets to a and is less than a, the closer f of x gets to L. Okay? Same thing on the right limit. So the limit as f of x approaches a from the right means as x approaches a, but is still greater than a, right, bigger than a, f of x approaches L. And that second part doesn't matter if it's from the left or from the right, just x. Okay, here's graphically, right? Same idea. We're only picking, so here's a, x is approaching a from the left, so we're only allowed to choose x values that are to the left of a. And here, same thing. Here's a, this is the fixed point that x is approaching. We're choosing x values here that are close to, but to the right of a. Let's look f of x. It is very close to L right here. Okay? Stop and give this a look if you need. This is a very important idea. That means to say that the limit of f of x as x approaches a equals L if and only if both limits, the left-hand limit and the right-hand limit, are L. Okay, they both have to exist and they have to be L. Okay, it's a very important idea. That makes sense, right? Because on that first, the one that I squared and read, I was allowed to pick any of the two sides. I was allowed to pick any x and plug into the function to see if it was close to L or not, right? And so if I'm allowed to choose any of the two, less or greater than, and I still get close to L, then that means both of these on the right have to be, from the left and from the right, both limits have to be L. I'm going to talk more about this. This is just intuition for today. Okay, let's do an example graphically. So I have a function g, and let's use this value, this graph, to find some values of limits. Okay, so let's talk about a first. A is telling me that I'm plugging in x values that are very, very close to -2. So where's -2? Here's let me say it again. We're getting x values that are very, very close to 2, but less than 2. So we're picking values over here, right? So if I follow the graph of the function, I'm getting very, very close to 3. You see? Very, very, very close to 3. Okay? So the limit, as x approaches 2 from the left of g of x, that equals 3. Okay? Take a second to understand this if you need to. Change colors. Let's go purple. B is saying x is approaching 2 from the right, so I'm to the right of 2, but still very close to 2. I look at the graph, I'm very, very close to this height, which is 1 here, right? So that means the limit as x approaches 2 from the right of g of x equals to 1. Okay? So f of this guy here, right, that is very, very close to 1. And the closer I get to 2, the closer that height gets to 1. Okay? Change colors again, go green. As x goes to 2, what's the limit? Remember what I just said, right? In the previous slide. For the limit to exist, limit as x approaches 2 exist, at both sided limits, both one-sided limits have to exist, and they have to be equal. Now they both exist, but they're different. So that means this guy does not exist because, and I'll say, the limit x approaches 2 from the left of g of x is not equal to the limit as x approaches 2 from the right of g of x. They both exist, but they're different. Okay? We'll talk about how they could not exist soon. But they'd have to be different. They'd have to be equal for the limit to exist. The idea that I'm talking about is like, okay, this is asking me to pick values that are closer and closer to 2, and I see what g of those values is, you know? And if I choose like 2.1, then I get one value, like 3.1 or something. But then if I choose like 1.9 on the left of 2, then I get something closer to 1, or vice versa, right? I get two values that are very distinct, very far apart. It's not getting closer and closer to anything. Yeah. So let's talk about D now. Go back in colors to blue so that you can easily distinguish between each item. Okay, so D is telling me that I'm supposed to choose x very close to 5 and to the left of 5. So here's what it is. Supposed to get very, very close to this, which is, I guess, 2 here, right? This is 2. So I'll say the limit as x approaches 5 from the left of g of x equals to 2. The limit x approaches 5 from the right of g of x equal to, said I was going to change colors, right? So let me change back to purple. Limit x approaches 5 from the right, g of x. I look at the graph. So I'm close to 5, but to the right of 5, still close to 2. Right? There's no jump. We call this a jump. What happened at 2? That was a jump. There's no jump at 5. So I'm still close to 2 here. So because these are equal this time, then this is also 2. Okay? These are equal. Okay? So this is because limit x approaches 5 from the left of g of x equals the limit x approaches 5 from the right of g of x, and both are 2. So the answer for the limit as x approaches 5 without choosing a particular side equals 2 as well. Okay, note here that f of, not f, g of 5, so this I can write, it's like an observation, g of 5 equals to 1, right? G of 5 is 1, which is where the filled in circle is, whereas g of 2 is undefined. We don't care. When we talk about limits, we don't care about g of 5 or g of 2. The point where we're going to, we don't care what happens there. We care about what happens around that point. Okay, let's keep going. Extend this a little bit, so let me go a little bit faster. How can a limit fail to exist? If the graph is ugly enough, this could happen. So let's talk about this. Let's talk about this actual value here. Notice that the function f of x equals pi over x is undefined at 0, right? You can't divide pi by 0, so you can't plug in x equals to 0. So how do we guess, like, again, quotation marks, what's f of 0 if we can't calculate what it is, we choose x values closer and closer to 0. And here's what they're doing here, like 1, 1/3, 1/2, 1/4, 0.1, 0.01. And all these values, calculate all these values, get 0. F of those guys, they're all 0. So a person would guess, right? See, 0.0001, that's 0. That's not close to 0, that's 0. So a person would guess, okay, that means, the limit, we would guess, so we guess that the limit x approaches 0 sine pi over x equal to 0. We would guess that if we chose those values to plug in. However, that's not true, because if you graph the function, that's how wild it looks. You can use like a graphing calculator if you want. May depend on how powerful a calculator is. You may sort of break it for a second, may cause it to have an error. You can use wolframalpha.com. That's something that I like. I'll show you how to use it a couple more times. But if you want to go ahead and try it out yourself, you can go wolframalpha.com, and you can say, you can just say plot. Type in the box. You can plot. Type plot sine, pi divided by x, and you're gonna see that it's gonna plot you this very ugly looking, and there's no limit, because depending on what you choose, right? Like we're if I zoom in, we were being unlucky and we were choosing all of these points here, right? And they are all 0. But if I choose something that's very, very close to 0, I can still have something that equals 1, or I can still have something that equals -1. Right? There's no one value that the f approaches as I get closer and closer to 0. Okay? Again, if this is a new idea, stop, think about it. And this is the solution. The limit does not exist. Okay? Let's talk about infinite limits. Again, close up the intuition on this. Infinite limits happen when, rather than approaching a given value, as you choose x values closer and closer to a, f of x gets very, very large, or very, very small, like very, very negative, like -1,000, -1,000,000, -1,000,000,000, gets very, very negative, or very large positive, like 1,000, 1,000,000, 1,000,000,000, a trillion, whatever. Okay, so that's the idea. As x gets closer and closer to a, f of x gets larger and larger. Okay, and they use the word arbitrarily large, or as large as we please, another fancy way of putting it. Okay, always remember x not equal a, just getting closer to a. So this guy's not a number. This guy's just a symbol that means what we're saying, right? That means f of x is getting large. This is not a number. So a lot of the times we're going to do some, makeshift math with it, but we're not supposed to. So whenever I use this guy, I use like quotation marks when I do math with this. We don't need quotation marks in this expression, nor in this notation here. But whenever I do math, like, infinity divided by this or by that, I will like use quotation marks, because this guy is not a number. Just really drill that in. And this is the idea. This is the graph where this happens, right? If I choose x here, I got this value. If I choose x closer to a, I got this higher value. If I choose x closer to a, I got this even higher value. And based on how the graph is supposed to continue for an asymptote, right? The closer I choose, the higher the value that I get. So this is what this expression is telling me. Okay? The closer I choose, the closer to x that I, say it again, the closer to a that I choose x, the larger f of x is. Right? Take a second to understand what I said. And then this would be minus infinity. Same thing happening, but f of x having negative values, but still very, very negative. Like I said, -100, 1,000,000, 1,000,000,000, 1,000. A billion being larger than 1,000. And this is the intuition again. So here's an example, right? here's an example. This is actually true. The limit of as x goes to 0 of minus 1 over x squared, that is minus infinity, because if you choose, let's say, f of, I don't know, 0.1, I'll use my calculator, that will be, so first of all, I'll define, right, f of x will be the thing inside the limit, right? So I'll say f of x equals to minus 1 over x squared. If I do f of 0.1, that's going to be minus 1 over 0.1 squared. That's minus 1 over 0.01. And if you do that in the calculator, it's going to be 100. But then if you choose like something that's very, very small, like very, very, very close to 0, I think my math is off here by a couple decimal places. Let me actually do the calculator. Yeah, I think I have... No, I think I was right. Sorry about that. I think I was right. But here you end up getting like double the decimal places in zeros. So you get 1, 2, 3, 4, 5, 6, 7, 8 with a negative sign. So I think that's what you get. Double check. But this is huge. Okay, I'm getting like a very, very close x value to 0 and getting closer to 0. But the answers, the outputs are getting very, very large and the negative. So I write this. Okay, so we have an infinite limit here. Minus infinity, we say. Okay, so say the limit of f of x as x approaches 0 equals minus infinity. Okay, they say negative infinity is like the fancier way. Minus infinity is fine. Try and say negative infinity more often than not, but I may not say it. So just to close it up, we've talked about asymptotes before. Asymptotes here will be, these lines. If we talk about asymptotes, and when I say we talked about it before, I say, Math 141. We've talked about asymptotes in those pre-calculus classes, and we always talk about, the graph getting closer and closer to the line, but now we're going to be giving a precise definition, and this is the precise definition. Again, this is something to write down. We have an asymptote at x equals to 0 if, x, limit of f of x as x approaches a from the left or from the right equals to plus or minus infinity. So when one of these four cases happens, then we have a vertical asymptote. A vertical asymptote. Horizontal asymptotes are different. We're going to talk about them later on. But these are the four cases. We're approaching a from the left, and x is getting larger, so limit is plus infinity from the left. Right? See the little minus sign on top of a. If we approach from the right, limit equals plus infinity as well, because we're going up, right? That's why it's plus infinity. Here, we're going down and we're approaching from the left. So x approaching from the left with a little minus sign equals minus infinity. And here, we're approaching from the right going down. So x approaching from the right with a little plus sign and equals minus infinity because we're going down. Look at the four cases, understand them. Make sure you got it. And this is the definition that I talked about, okay, for vertical asymptotes. If one of these cases happens, any of these 6 cases happens, in a case, these are unnecessary. I'll keep them here because that's what the book does. But, they are included in the other 4. But if one of these cases happens, then we have a vertical asymptote, which is one of the situations graphically from the previous slide. Excuse me. Let's talk about this fairly quickly. We're almost done. Let's talk about this. So I have vertical asymptotes of f of x equals tangent x. So what we do is first we sort of classify and find possible places where we could have this happen. And the possible place where this happens is where the bottom equals 0. So let's find where cosine x equals 0. Right? And this is what we're doing. When is that equals 0, right? So if you remember the graph of cosine, or the unit circle if you want, where cosine is this, is the x axis on the unit circle. cosine equals 0 at 90 degrees, or at pi over 2. X equals pi over 2. Right? Or at x equals to 3 pi over 2. And whenever you add, plus 2 pi n. So if you don't remember this from Math 142, take a second maybe to review what I'm saying, right? I'm talking about the two angles, 90 and 270, excuse me. And then you're adding 360 because it could be any full turn around the unit circle from those points. And now you're saying what happens, to tangent x if I choose values closer and closer to pi over 2. Right? And in fact, if you do, so let's say what pi over 2 is in a calculator, just so I can tell you. Okay, so pi, it should be 1.5-ish, right? 5.5-ish, 5.7-ish, but I just want to make sure. So I get, where's my pi here? Can't find pi in my calculator. Yeah, found it. Pi divided by 2. It's like 1.5707, let's say. So let's say I choose, x value very close to pi over 2, which is like 1.57, right? So, and I find f of x, right? So like tangent of x. So this is tangent of 1.57. So I'll do that. Where's tangent? Tangent 1.57. So this is like 1,255 point something, 0.8-ish. But what if I choose something even closer to pi over 2, which is like, I do the math at pi over 2 again, just so I get something closer. So I'm just looking at the calculator and looking at more decimal places. So if I do 1.5707, and I got the feeling that's not going to fit, right? So I do tangent of 1.5707. And that will be 10,000 10,381.3-ish. So that's much larger. And you're going to see that the more decimal places for pi over 2 you use, the larger this gets. So this is getting larger and larger as this is getting closer and closer to pi over 2. Okay? So it is fair to say that the limit is infinity. So any of these two things, and therefore, you have asymptotes at pi over 2, at minus pi over 2, and everything else. Okay? I'll stop here, trying to absorb these ideas. Thank you for watching all that.